Global capacity for wind and solar energy is expanding at a staggering rate, bringing vast amounts of clean electricity to grids around the world. The natural assumption is that as this generation capacity scales up, we will simply build giant lithium-ion battery farms to catch and hold all of the excess power. But sunshine and wind operate on their own natural schedules, and those schedules rarely line up with the moments we actually need to turn on our heaters or air conditioners. Bridging the gap between when power is generated and when it is consumed introduces a severe mathematical problem of time. On a scale of hours, standard lithium-ion batteries perform perfectly. You catch the midday sun with solar panels, and you discharge that stored energy when people get home from work in the evening. This chart shows a 7-day window. A windless lull rapidly drains battery reserves, leaving a gap where demand outpaces generation. Expanding out to 12 months reveals a severe mathematical problem, a massive seasonal gap between extreme summer generation and extreme winter demand. We cannot mine enough raw lithium to build grid-scale battery farms that are designed to charge up in July, only to sit entirely idle for 6 months waiting for January. The physical constraints and the economic costs make it impossible. Batteries cannot survive the math of long-duration storage. That leaves seasonal storage. The grid has to pivot away from storing trapped electrons and move towards storing physical chemistry. The process starts when wind and solar generate more power than the grid immediately needs. That surplus electricity is actively diverted away from the grid and entirely bypasses those overloaded battery farms. Instead, the power is routed into synthesis plants. You can think of these facilities as clean energy refineries. As this flowchart outlines, that clean electricity acts as the single input. The synthesis plant uses that current to drive a chemical reaction, converting the raw power into distinct molecular outputs: hydrogen, methanol, synthetic methane, and synthetic hydrocarbons. By forcing this chemical conversion, highly ephemeral, weather-dependent electricity is trapped into a permanent physical state. Standard battery cells are subject to constant physical decay. They slowly leak and lose their charge the longer they sit. Chemical bonds do not. In a side-by-side comparison, a standard battery depletes over a 6-month timeline, while synthetic fuel remains locked at 100% from summer to winter. Shifting to physical volume, a single compact storage tank yields the exact same energy output as a sprawling 1-gigawatt battery farm. Converting electricity into chemical bonds neutralizes the time problem. We can stockpile vast reserves of energy for years without losing power to decay. Because these synthetic molecules exist as liquids and gases, they are subject to the same global shipping and transport logistics as traditional fuels. This solves the geographic isolation of clean energy. Power generated in optimal but highly remote locations, like deep ocean wind turbines or deserts, can now be easily moved directly to dense population centers. Moving this energy physically means we avoid the impossible task of permitting and building new intercontinental electrical transmission grids. This global map illustrates the alternative. Instead of relying on fragile, localized electrical grids, we can transport these synthetic molecules using existing global infrastructure: international pipelines, maritime shipping lanes, and massive industrial storage tanks. Synthetic fuels effectively transform the clean power grid into a highly robust global supply chain. Once those shipped synthetic fuels arrive at their destination, they can directly support heavy global industries. Aviation and maritime shipping physically cannot run on raw battery power, but they are perfectly suited to burn these clean, dense liquids. The public vision of a fully renewable future usually involves endless fields of sleek, high-tech batteries humming silently under the sun. The pragmatic, physical requirements of true long-duration storage look much more industrial. The largest long-duration energy platforms of tomorrow will look almost indistinguishable from the fuel depots and shipping ports of the 20th century. We are taking the heavy, sprawling infrastructure of the old energy system and repurposing it to serve as a permanent, reliable reservoir for clean power.